This is problem 1.5.9. It tells us that we have 17 light bulbs in a box of 100 that are broken, and we want to select 3 at random. It asks us to draw a probability tree for this problem, and then asks what is the probability that there are no broken light bulbs. That would be the probability that x equals 0. Or, sorry, we haven't gotten to that point yet in this class. That would be the probability of 0 broken. And what is the probability that there will be no more than 1 broken light bulb? If you think about to get 1 broken light bulb, then that means you're going to have 0 or 1 broken. Either one of those would be what you want it to be. Now, you don't have to have a probability tree. I could probably just sit down and figure this out. But if you're having trouble figuring out what the possible outcomes are, a probability tree can really help. So I'll go ahead and draw this out. If you feel like you're good on the probability tree, you can skip ahead in the video until I'm done with the tree. Okay. So what we're going to do is we're going to have kind of our first draw, our second draw, and our third draw. So to start off, I have 2 choices when I draw. I can get a good bulb. So I'm going to use abbreviations G equals good and B equals broken. So I can either get a good one the first time or a broken one. Now the next time I draw, I can either get a good or a broken. And the third time I draw, I can get good or broken, good or broken. Well, let's say I got broken the first time. Well, the next time I draw, I can still get good or broken. And then the third time I can get good or broken and good or broken. So those are all of my possibilities. I have 3 draws. Every time I can get good or broken. Now I can go through and fill out all of the probabilities. Well, it tells us that 17 in a box of 100 are broken. So broken, we're going to start at 17 out of 100 will be my starting value. For good, well, if there's 17 broken out of 100, I can do 1 minus that and realize that there are 83 out of 100 that are good. So for my first draw, if I want a good one, I have 83 out of 100 to choose from. For my first broken one, I would have 17 out of 100. So first draw, we're only drawing out 1 bulb. It's either 83 or 17 out of 100. But now when we go to our second draw, we've used things. So if I was good first and now I want another good one, I've used 1 good one. So I'm going to be at 82 out of a total of 99 because I've taken 1 out. But let's say I wanted a broken one second. So I had a good one first, which means there are still 17 broken ones. But I took 1 out, so it's 99 total. Let's come down here. If I'd had broken first and then I want good, well, I used the broken one, so there's still 83 good. But a total of 99. If I had broken and then I want another broken one, well, I've already used the broken, so now there are 16 broken out of 99 total. So as you go through, you just have to be careful. You have to say, how many good have I already used? How many broken have I already used? What's left? Let's go to our third draw. If I had good and then good, and now I want another good, well, I've used 2 goods already. So we had 83 to choose from, then we had 82. Now we're going to be at 81 out of 98 total because we've used 2 light bulbs and they were both good. Let's say I wanted good, good, and then broken. Well, there would still be 17 broken because I haven't used any broken, but there are only 98 total because I already used 2 bulbs. And you go through and fill out the entire thing like this. I'm going to pause and fill out the rest so you can double check your work, pause and do the rest by yourself. Okay, if I did all of that correctly, it should look like this. Okay, now that you have a probability tree, it can be easier to figure out what probabilities you need later. Again, not required every time, but especially very useful if you're getting confused. So when I draw a probability tree, I can go through and write out all of my probabilities over here. So I could say if I wanted good, 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 the probability of good, good, good. Now when I write that, I really mean good and then good, but we don't always write that out explicitly every time, but that's what it means. It's good and good and good. So if we want an and, we're going to multiply. So for good, 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 it would be 83 out of 100 times 82 out of 99 times 81 out of 98. Because I follow the tree, I do good, 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 and I multiply all of those probabilities along the way. That's why probability tree is useful. We just multiply everything, and that's the total probability. Which in that case, that would be 0.5682. So the probability of getting good is 0.5682. Then I could do the next branch along the tree if I wanted. So like I could do good and then bad. So probability of good and one bad at the end is going to be, and now you just go through and multiply those. So we'd have 83 out of 100 times 82 out of 99 times, and then our last one now is 17 out of 98. And you can go through and do this for all 8 branches if you want. However, that might be a little bit of extra work. You might not actually need all of those. So let's go back to our problem. So we wanted the probability of 0 broken. Well, which branch up there gives you 0 broken? The branch up there that gives you 0 broken is the probability of good and good and good, which we already found out is 0.5682. Then it wants us to find the probability that there's no more than 1 broken, which we said is going to be 0 or 1 broken. So let's take an intermediate step and find what's the probability of 1 broken. Well, the probability of 1 broken, how are the different ways I can get 1 broken? There's a few different ways to do it. Let's find them all. To get 1 broken, I could do good, broken. Or I could do good, broken, good. Or I could do broken, good, good. So let's write those down. This would be the probability of good, broken, or good, broken, good, or let's see what I say, broken, good. Basically find all the different ways. So your broken one can come third, it can come second, it can come, oops, I wrote that one wrong. Broken, good. How about that? So you need 1 broken one, it can be third, second, or first. Now you have to find each of these probabilities individually, which we'll do by just multiplying along the tree. So find where they are on the tree and multiply those probabilities. So for good, broken, that's the one we just found up here. So that's going to be 83 out of 100 times 82 out of 99 times 17 out of 98. Now this is where if I didn't want to actually do the tree, I would just skip right to this step. I'd write out these are my 3 possibilities. And then I just find the probabilities based on saying, oh, well, I need good. That's going to be 83 out of 100. I need another good. That'll be 82 out of 99. And I do all my math that way. The tree is really helpful to make sure you actually write out all of your possibilities. So for just like 3 things, it's not very hard to just kind of do it in my head. If you're getting more complicated or you want 2 broken ones or something, it gets much more complicated. And then I really like the tree. For an or, whenever we have or, we'll do a plus. So now let's find good, bad, good. So that's going to be 83 out of 100 for my first good one. Then I want a bad, so there will be 17, but only 99 bulbs because I used 1. Then I want another good, but I've used 1 good, so it'll be 82 out of 98. Okay, plus, now I need bad, good, or broken, good. So there's 1 broken one to start with. Then I want a good one, and there's 83 good ones, but only 99 bulbs. And then I want another good one, but I've used 1, so 82 out of 98. Again, if I don't want to just do that in my head, I follow the tree. So bad is 17 out of 100. And then another good is 83 out of 99. And then, wait, I'm following the wrong path. Bad, good, oh, there we go. And good is 82 out of 98. Now, the interesting things about these problems that always happens is that when you look at these, notice the denominator is always 100, 99, 98. And the numerator is always 83, 82, and 17. It might just change the order, but the numbers are still the same. So every one of these is going to be exactly the same, which is pretty cool when you're doing this specific kind where you're looking for like 1 good or 1 broken, 2 good. So I find the probability, or instead of adding them up, I can just do 3 times, let's see, each individual one was 0.1193. I did 3 times because I realized each of these is exactly the same. If you don't know for sure if it will be, or you don't want to mess up on a different problem that's not the same, just multiply them all out and you'll see they're all the same. And so we get 3 times that gives me 0.3579. Now that I have that, we can finish off the problem finally. So the probability of 0 or 1 broken is we're just going to add those two numbers together. So that's just going to be the probability of 0 broken plus the probability of 1 broken. So 0.5682 plus 0.3579 gives me 0.9261.